February 19th, 1945. Iwo Jima's volcanic sand. 0530 hours. Marine Corporal Danny Morrison crouched behind a Sherman tank that bore little resemblance to the standard medium tanks that had carried American forces across Europe. Instead of the familiar 75mm gun barrel protruding from its turret, this machine mounted a weapon that would have looked more at home in a medieval siege than modern mechanized warfare. The M4A3R3 flamethrower tank, officially designated Zippo by the Marines who would follow it into hell, represented 4 years of American engineering evolution, driven by the brutal realities of Pacific Island warfare. Morrison had witnessed the birth of desperation 3 islands on earlier Tarawa, where Japanese defenders had transformed fortresses that conventional coral atolls into underground artillery could not tank guns touch. Stander-fired projectiles that expel contact with reinforced concrete, leaving defenders unharmed in tunnels 30 feet below the surface. Infantry assaults against positions that artillery had failed to suppress resulted in casualty rates that made traditional military mathematics obsolete. Something fundamental had to change, or the Pacific Campaign entire would consume Marine divisions without achieving tactical. The FL Objectives M-thrower tank that Morrison now sheltered behind represented the American military's answer to fortress warfare that conventional weapons could not penetrate. But the path from concept to battlefield deployment had been paved with technical failures, bureaucratic resistance, and engineering challenges that nearly killed the program before Japanese tunnels proved its necessity. The story weapon began 18 months earlier in A of how flame became America's most feared battlefield Detroit factory, where automotive engineers struggled to transform into practical instruments theoretical concepts of war. Chemical Warfare Service Major William Patterson stood in the experimental weapons facility of the Chrysler Tank Arsenal on August 12, 1943, watching technicians mount equipment that violated every principle of conventional armored warfare. The standard Sherman tank before him had been stripped of its main gun and fitted with a flame projector system that could theoretically deliver burning fuel at temperatures exceeding 2,000 degrees Fahrenheit across ranges that extended beyond rifle fire. The engineering was ambitious. The tactical application remained unproven. The political implications were troubling to keeping enough Pentagon officials awake at night. Patterson possessed the methodical bearing of a career officer who had spent 15 years studying chemical weapons treaties and international law. His West Point education had emphasized the importance of maintaining moral authority in warfare, but Pacific theater reports painted increasingly desperate pictures of Japanese defensive tactics that made conventional assault methods suicidal for attacking forces. Intelligence estimates suggested that Iwo Jima's garrison had constructed over 11 miles of interconnected tunnels, creating a subterranean fortress that could shelter 21,000 defenders indefinitely, while maintaining fields of fire that covered every possible landing beach. The flame projector mounted in the Sherman's turret represented months of developmental work by engineers who had never witnessed combat but understood the mathematical requirements of fortress warfare. The system used compressed carbon dioxide to propel napalm mixture through a reinforced nozzle at velocities that created effective ranges approaching 150 yards. Fuel capacity allowed for 60 seconds of continuous flame projection, theoretically sufficient to clear multiple defensive positions during a single engagement. But theoretical capability meant nothing if the equipment failed under combat conditions where mechanical breakdown resulted in crew death rather than maintenance delays. Staff Sergeant Michael Romano approached the experimental tank with the skeptical expression of a career tanker who had learned to distrust innovations that complicated proven systems. 20 years of armoured service had taught him that reliability trumped sophistication when crews operated under conditions where enemy fire made field repairs impossible. The flame system added 800 pounds of equipment to the Sherman's fighting compartment, while removing the main gun that provided long-range defensive capability against enemy armour. Any technical failure would leave that advertised its vulnerability through the crew defenceless in a vehicle specialised equipment that marked it for priority targeting. The first test firing revealed problems that would plague flamethrower development throughout 1943 and into early 1944. The fuel mixture ignited prematurely in fire that threatened the barrel, creating bacti to incinerate the crew compartment. Pressure fluctuations caused by temperature variations made range estimation impossible under field conditions. Most critically, the flame projector's limited traverse forced tank commanders to expose their vehicles to enemy fire while maneuvering for optimal firing positions. Patterson documented every failure with meticulous precision, understanding that developmental problems discovered in Detroit testing were preferable to mechanical breakdowns that occurred during chemical warfare. Background provided context for equipment combat operations. His limitations that could be addressed through engineering refinements, but only if testing protocols identified weaknesses before tanks reached operational theaters where ended on equipment reliability. Crew Survival (DP). The breakthrough came during October testing when Chrysler engineers solved the backfire problem through redesigned systems that eliminated pressure spikes responsible for premature ignition. New effective range to nearly consistency, while extending napalm formulations improved 200 yards under, importantly, revise optimal conditions. Most traverse mechanisms allowed Flemex without projection across broader air, exposing tank holes to enemy fire from. By multiple directions simultaneously, December 1943, the M4A3R3 had achieved performance specifications that satisfied chemical warfare service requirements, while maintaining mechanical reliability standards demanded by armoured units that operated far from maintenance facilities. Production authorization arrived from the War Department on January 8, 1944, with orders for immediate manufacture of 150 flamethrower tanks designated for Pacific Theater operations, where conventional weapons had proven inadequate against fortified positions. But engineering success in Detroit factories meant nothing if tactical doctrine failed to integrate new weapons effectively into existing operational procedures. Marine Corps commanders faced fundamental questions about how flamethrower tanks should be employed in amphibious assaults where coordination between infantry, artillery and armour determined success or failure of entire operations. The weapon was revolutionary. The tactics for using it remained theoretical constructs developed by officers who had never witnessed flame warfare under combat conditions. Lieutenant Colonel James Mitchell arrived at Camp Pendleton in February 1944 to establish training protocols for crews who would operate America's newest battlefield weapon against Japanese positions that conventional arms could not reduce. His tank warfare background provided understanding of armoured operations, but flamethrower tactics stead territory where mistakes would be measure represented uncharred tank training possessed in lives rather than mechanical failures. The Marines' combat experience from selected for Flame Guadalcanal and Nawa, but non-tarred specialized had operate different tactical approaches from weapons that required completely standard tank warfare. The training program that emerged at Pendleton would prepare crews for warfare unlike anything American forces had previously encountered. Mock Japanese positions constructed from concrete and steel simulated the underground fortifications that intelligence reports described across potential invasion targets. Live fire exercises using actual palm reveal ENAD tactical limitations that textbook studies had not anticipated. Range forced flame restrictions tanks to operate within enemy small arms range. Fuel consumption limited engagement deammunition. Duration to 60 seconds maximum. Most critically, specialized made flame tanks dependent lines that could be disrupted by enemy on-supply action. The tactical that evolved between flame tanks and supporting doctrine through months of training emphasized coordination infantry that would provide protection against enemy forces targeting the specialized vehicles. Standard procedure required conventional Sherman tanks to suppress enemy positions, while flamethrower variants maneuvered into firing positions. Infantryed flame tanks to squads would advance behind occupied positions cleared by fire. Artillery would provide covering fire during withdrawal phases when fuel exhaustion left flame tanks vulnerable to counterattack. As 1944 progressed toward its violent conclusion, flame tanks completed training and began shipping toward Pacific staging areas where they would await deployment against targets that aerial reconnaissance had identified as impervious to conventional bombardment. The weapon was ready, the crews were trained, the tactical integration had been tested under simulated combat conditions. But nobody knew whether American flame warfare would prove decisive against Japanese defensive systems that had been specifically designed to defeat methods through underground conventional assault construction that eliminated traditional targets. The USS Terror anchored off Iwo Jima's southeast coast on February 16th, 1945, her cargo holds containing the first operational deployment of flame warfare define how technology that would risk American forces approached decks, 30'd fortress combat. Below secured in transport Hroa tanks sat 6 M4A3R3 Flamet cradles, while their crews made final preparations for an assault that would test 4 years of developmental engineering against Japanese defensive systems specifically designed to defeat conventional military operations. Sergeant Robert. Technical Chen stood beside flame tank F7 Hands along fuel lines that carry, running his napalm mixture from tanks to the turret's internal storage-mounted projector system. His mechanical engineering background from Berkeley provided understanding of hydraulic systems and pressure dynamics days of rough, but 3Cs had created maintenance challenges that no peacetime testing had anticipated. Salt spray had corroded electrical connections, while constant vibration had loose adjustment-tuned fittings that required precision-maintain proper fuel flow rates. The flame projector itself, trialment by Chrysler engineers who had solved and error testing, represented months of refined fundamental problems through fuel mixins of experimental of gall that consumed thousands churs. The napalm formula finalosity that allowed effective projection maintaining viscosity, while temperatures that exceeded 2,000 degrees Fahrenheit achieved burning across ranges approaching yards under optimal 200 conditions. But optimal conditions meant calm weather, level terrain, and absence of enemy fire. Side none of these advantages would Jima promise Kowalski emerge. Staff Sergeant Tony's interior carrying maintenance from the tank that documented every component inspection, complete logs crossing during the Pacific. His Detroit assembly line experience had taught him that mechanical reliability under stress depended on methodical attention to details that inexperienced crews might overlook. The flame system added complexity that multiplied potential failure points while operating under conditions where breakdown meant crew death rather than mission delay. Each flamethrower tank carried 290 gallons of napalm in pressurized storage tanks that fed the projector system through reinforced fuel lines protected by armored conduits. Carbon dioxide pressure bottles provided projection force, while electrical ignition systems created the spark that transformed liquid fuel into directed flame. The entire system represented engineering sophistication that impressed Pentagon observers, but worried field mechanics who understood that complexity was the enemy of battlefield reliability. Found Chen Anlight in the pre-Corporal Morrison Kowalski, reviewing technical specifications by flash-dawn darkness of February 19th. The landing craft engines had been warming up for 30 minutes while naval gunfire pounded Japanese Atori bombardment that positions with pre-power created artificial sunrise across Iwo Jima's volcanic landscape. Intelligence reports indicated that American naval artillery had expended more ordnance during the preliminary bombardment than any, yet previous Pacific Operation reconnaissance photographs showed to enemy minimal damage positions. The Japanese defensive from previous defeats had learned to construct fortifications that absorbed conventional bombardment while preserving defensive capability through underground construction techniques that American engineers were only beginning to understand. Concrete reinforced tunnels connected firing positions that could be sealed during artillery reopened when strikes in American infantry began their assault. Machine gun emplacements possessed overlapping fields of fire that covered every approach route while remaining invisible to aerial observation until Marines advanced within killing range. Chen final time as checked fuel to higher pressure gauges one landing craft engines shifter RPMs, signaling immediate departure toward beaches where flame warfare would receive its first operational test against fortress construction that had defied months of conventional bombardment. His slide rule calculations had confirmed that napalm projection at maximum range consumed fuel at rates that limited engagement, continuous fire duration to 60 seconds of. Every second would count when Japanese defenders emerged from underground positions that artillery had failed to reduce. The landing craft's metal deck vibrated with mechanical rain against Pacific energy as engines sent swells that threatened out the over to tons of arm-loaded vessels carrying 30-odd vehicle plus crew equipment toward a beach that intelligence estimates suggested was to conventional assault methods defended by positions immune. Morrison watched through the craft's narrow vision ports as Iwo Jima's distinctive silhouette grew volcanic peaks larger against the dawn sky. It's shrouded in smoke from naval gunfire that had accomplished little excepting defenders to American alert intentions. Kowalski made final adjustments to ignition systems while explaining procedures that would determine whether flame projection succeeded or failed during the crucial moments when crews engaged targets that standard tank guns could not affect. The electrical components that created ignition spark had been waterproofed against salt spray, but landing operations would subject every system to conditions that exceeded design specifications. Moisture infiltration could prevent ignition, while mechanical shock might disrupt fuel flow at precisely the moment when flame projection was most critical. The flame tanks that approached Iwo Jima represented more than technological innovation. They embodied American industrial adaptation to warfare that conventional through traditional weapons could not resolve applications of firepower and maneuver. Japanese had evolved defensive construction beyond the reach of artillery bombardment and tank guns, creating tactical problems that demanded entirely new approaches to fortress reduction. Flame warfare offered solutions, but only if engineering reliability matched theoretical capability under conditions where failure meant tactical defeat. D. The beach designated green. As landing craft approached 1, Chen observed Japanese defensive positions that aerial reconnaissance had failed to identify completely. Concrete emplacements emerged from volcanic rock with camouflage that made target identification impossible until machine gun fire revealed actual positions. The underground construction that intelligence reports had described appeared even more extensive than American estimates had suggested, creating a defensive system punishment while maintaining operational effectiveness. That could absorb tremendous ramp dropped at 0630 hours, exposing Morrison tank to enemy's flamefire that immediately demonstrated why conventional tactics had failed during previous Pacific operations. Japanese defenders possessed clear observation of the entire landing zone, while remaining concealed in positions that standard weapons could not reach. Machine gun fire from multiple directions created crossfire patterns that pinned infantry units against the beach, while mortar rounds bracketed landing craft still approaching the shore. Morrison volcanic sand grab engaged the Sherman's transmission ASD at tracks designed for European terrain, rather than Pacific beaches where loose volcanic material created traction problems that American tank designers had never anticipated. The flame tank's additional weight from napalm storage and projection equipment made beach mobility even more difficult, while specialized armor modifications reduced ground clearance that complicated movement across terrain obstacles. Chen monitored fuel system pressure as the tank struggled inland toward positions that aerial photographs had identified as primary defensive strongpoints. Intelligence estimates had Japanese construction proven conservative regarding techniques. The concrete fortifications were more extensive camouflage than American planned better CAM-D. Conventioners had anticipated bombardment had failed to suppress positions that remain artillery fire, FROMmed operational, despite weeks of pre-pair naval guns and aircraft. The first tactical employment of American flame tanks was about to begin under conditions that would determine whether 4 years of developmental engineering could solve fortress warfare problems that conventional weapons had proven inadequate to address. Japanese positions specifically designed to defeat American assault defenders waited in underground methods, while Marine crews prepared to test whether flame projection could accomplish what artillery bombardment and tank guns had failed to achieve through months of Pacific Island warfare. The first flame tank engagement began at 0635 hours as Morrison's Sherman crested a volcanic ridge that revealed the tactical nightmare facing Marine assault units. Japanese machine gun positions emerged from camouflaged firing ports with interlocking fields of fire that covered every approach route while remaining invisible until muzzle flashes betrayed their locations. Standard Sherman tanks had already expended hundreds of rounds against concrete emplacements that absorbed direct hits from 75mm guns without reducing defensive effectiveness. Artillery observers reported frustrated attempts to suppress positions that disappeared underground between bombardment missions, only to re-emerge when infantry advanced within killing range. Chen activated the flame projector system as Japanese small arms fire began impacting against the Sherman's frontal armor, with metallic percussion that announced their presence to every defender on the island. His Berkeley engineering education provided theoretical understanding of hydraulic pressure dynamics, but combat conditions introduced variables that laboratory testing had never simulated. Vibration from enemy fire disrupted fuel flow calibration, while volcanic dust infiltrated ignition systems through ventilation ports that peacetime designers had never sealed against battlefield contamination. The napalm mixture that emerged from the turret-mounted projector created a directed stream of burning fuel that extended across terrain where Japanese defenders had constructed firing positions specifically designed to defeat conventional weapons. At maximum range, flame projection achieved distances approaching 180 yards under combat conditions that included crosswinds and target elevation differences that affected fuel trajectory calculations. The burning napalm adhered to concrete surfaces while generating temperatures that exceeded 2,000 degrees Fahrenheit, creating thermal conditions that made underground positions uninhabitable, regardless of structural protection. Staff Sergeant Kowalski observed the tactical effect through periscope vision that provided limited observation of target areas, while protecting crew members from sniper fire that had already disabled 2 conventional tanks supporting the flamethrower operation. Japanese positions that had withstood direct artillery hits began showing signs of thermal distress as napalm penetrated firing ports and ventilation systems that connected surface emplacements to underground tunnel networks. Concrete began spalling under extreme heat while steel reinforcement expanded beyond design tolerances, creating structural failures that conventional bombardment had not achieved. The psychological impact proved equally devastating as Japanese defenders discovered that underground construction provided no protection against weapons that transformed enclosed spaces into furnaces. Intelligence reports from previous operations had documented Japanese willingness to fight from prepared positions until physically eliminated by direct assault. Flame projection created tactical conditions where defensive positions became uninhabitable without requiring infantry to advance across terrains swept by machine gun fire from multiple concealed locations. Technical Sergeant Romano monitored fuel consumption rates that limited engagement duration to periods measured in seconds rather than minutes. Each flame projection consumed napalm at rates that made tactical planning critical for maximizing effectiveness while conserving fuel for subsequent targets. The 290 gallons of napalm carried internally provided sufficient fuel for 12 separate flame projections at maximum range, requiring precise target selection and coordination with supporting infantry that would occupy cleared positions before Japanese defenders could re-establish defensive control. The tactical coordinations extensively during training squads had been rehearsed between flame tanks and infantry timing challenges that pieced flame tanks discovered that Japanese positions anticipated. Marine rifle at Camp Pendleton, but combat conditions introduce time exercises had not companies advancing behind possessed backup firing ports that remained operational even after primary emplacements had been neutralized by flame projection. Secondary defensive positions required additional flame attacks that consumed fuel reserves while exposing tanks to enemy fire from directions that initial reconnaissance had not identified. Corporal Morrison maneuvered the Sherman across volcanic terrain that created navigation challenges for tanks designed to operate on European roads, rather than Pacific beaches, where loose, volcanic sand provided inadequate traction for tracked vehicles, carrying additional weight from specialized equipment. The flame projector system added 800 pounds of equipment, while fuel storage tanks contributed another 2,400 pounds of combat weight that reduced mobility across terrain where conventional tanks already struggled with ground pressure problems. The underground tunnel system that connected Japanese defensive positions proved more extensive than American intelligence estimates had suggested. Flame attacks against individual emplacements often failed to neutralize entire defensive complexes because underground construction allowed defenders to evacuate burning positions while maintaining operational capability from alternate firing points. The tactical solution required coordinated flame attacks against multiple positions simultaneously, creating logistical demands that exceeded the fuel capacity of individual tanks while requiring tactical coordination that strained communication systems under combat stress. Chen's fuel pressure monitoring revealed projection of finited consumption rates that made flame tactical resource requiring careful management throughout extended engagements. Each second of continuous flame palm at rates calculate projection consume NAD through slide rule mathematics that translated theoretical fuel capacity into practical engagement, effectiveness, limitations. Maximum demanded flame projection in concentrated bursts rather than continuous streams, allowing thermal penetration while conserving fuel for subsequent targets that intelligence reports suggested numbered in. The tactical doctrine hundreds rather than dozens that emerged during the first hours of flame-tanked coordination between specialized employment, emphasized vehicles, and conventional armor that provided long-range fire support, while flame maneuvered into positions tanks where thermal weapons could achieve maximum effectiveness. Standard Sherman tanks suppressed enemy positions with 75mm gunfire, while flamethrower variants approached within effective range of defensive emplacements that artillery bomberized throughment had failed to neutral conventional explosive effects. Japanese defensive construction had anticipated conventional American assault methods through underground tunnel networks that provided protection of fire that covered all against artillery bombardment while maintaining fields' possible approach routes. The fortress warfare techniques employed on Iwo Jima represented evolutionary development from previous Pacific battles, where Japanese engineers had learned to construct positions that could absorb tremendous punishment while preserving operational capability through structural design that emphasized survival rather than comfort. The flame projector's limited traverse forced tank commanders to expose their vehicles to enemy fire, while maneuvering for optimal firing angles against targets that possess machine gun EMD. Multiple firing ports orient directions. Japanese placements had toward different approach been constructed with overlapping fields of fire that created crossfire zones impossible to avoid through tactical, requiring flame maneuver tanks to accept enemy fire while staff positioning for effective thermal fortifications. Attacks against concrete logs documented equipment performance under electrical systems, combat conditions that exceed Sergeant Kowalski's maintenance reliability DPD during developmental testing in Detroit facilities while volcanic dust infiltrate. SALT every specification established hydraulic component sols designed through SE theatre operations rather than Pacific Environments T. For European air corrosion-affected maintenance procedures that crews where abrasive-time engineering had not anticipated. Combat particles created maintenance challenges that P-sended on field performed under enemy fire that supplemented factory became apparent as using improvised techniques prescribed methods. The tactical began showing signs of thermal damage effectiveness of flame projection, Japanese positions that, placements uninhabitable, had resisted conventional weapons that rendered defensive empalm application, developed structural failures that compromised defensive exposed to sustained inner complexes. The fortress concrete surfaces circulation that distributed tunnel connections integrity, while underground vulnerable to thermal weapons that transform had defeated artillery, created thermalected defensive bombardment, became protective enclosure into tactical heat throughout intercon construction, that rifle companies advancing behind flame tanks discovered tactical liability. Marine provided during previous Pacific operations. Japanese defensive positions, neutral advantages that conventional weapons had not remained unionized by flame projection, habitable ford generating temperatures that prevented enemy re-extended periods while thermaled fortifications. The psychological residue continue as Japanese thermal weapons occupation of clear tactical areas affect extend defenders observed beyond immediate that made assault methods underground construction ineffective against American rest toward its violent conclusion, Flame Tank, as morning program operations revealed both capabilities and limitations that would influence tactical doctrine throughout the remainder of Pacific Theater operations. The thermal weapons proved devastatingly effective against fortified positions that conventional arms could not reduce, but fuel limitations and mechanical complexity created logistical challenges that required careful tactical planning to maximize combat effectiveness while maintaining operational sustainability, apply operations under conditions where RES faced constant enemy interference. The resupply challenge became Flame Tank had expended 7 apparent by 1,000 hours when Morrison, of its 12 possible fuel loads against Japanese positions that proved more numerous and intercon-cleared individual firing ports, while underground tunnel systems allowed defenders to re-establish operational capability from alternate positions within the same defensive complex. Technical Sergeant Romano calculated that complete neutralization of major Japanese strongpoints required coordinated flame attacks that exceeded the fuel capacity of single vehicles operating ECTID than intelligence estimates had predicted. Each napalm projection independently. Corporal Chen monitored hydraulic pressure readings that revealed mechanical stress beyond design specifications as repeated flame projections subjected the projector system to thermal cycling that peacetime testing had not simulated. The ignition components that created NAD within temperature ranges that approach palm combustion operated material failure limits, while volcanic dust infiltration created electrical resistance that threatened system reliability during extended operations. Combat conditions introduced maintenance requirements that field manuals had not addressed through standardized procedures. The tactical coordination between infantry revealed flame tanks and supporting timing challenges that training exercises at Camp Pendleton had not fully anticipated. Japanese defenders possessed secondary firing positions that remained concealed until primary eyes by thermal emplacements had been neutral weapons. Marine rifle squads advancing behind flame tanks discovered that cleared positions often concealed tunnel entrances that led to underground networks, defensive extending hundreds surface installations of yards beyond visible. The Fortress Construction Intelligence reports are described as individual that points proved to strongly interconnected, complex reductioners that required systematic than isolate rathered flame. Sergeant Kowalski observed Japanese attacks. Staff defensive tactics that adapted rapidly to American flame warfare through underground movement that allowed defenders to evacuate burning positions while maintaining operational locations capability from alternate. The thermal effectiveness that rendered individual emplacements uninhabitable did not eliminate defensive capability when tunnel systems permitted tactical withdrawal to prepared positions that remained undetected until infantry marine advanced within machine warfare demand gun range. Fortress did different tactical approaches than conventional armor operations, where position reduction meant permanent enemy elimination. The fuel consumption mathematics that Chen calculated through slide rule precision revealed logistical constraints that limited flame tank operations to short-duration engagements requiring immediate resupply or tactical withdrawal to protected areas where refueling could occur without enemy interference. Each complete fuel load provided sufficient napalm for approximately 15 minutes of tactical combat conditions that employment under-included maneuvering time between targets and positioning delays cause fire donned D by enemy. Sustained operations, major against complex defensives, required multiple flame tanks operating coordinated sequence in, while provide armor conventional fire. Sergeant Romano documented mechanical performance, technical, that exceeded reliability expectations, operating conditions that subjected every despited factory specifications. The flame projector system maintained component to stress levels beyond operational capability, while volcanic dust created abrasive conditions that affected mechanical components designed for European terrain, rather than Pacific environments where environmental factors introduced maintenance challenges that peacetime engineering had not anticipated. Combat proved that American industrial design could adapt to tactical requirements that exceeded original performance parameters. The underground that connected suppressive proved vulnerable to thermal weapons in ways that conventional explosives could not achieve through standard bombardment techniques, conditions within enclosed spaces that made habiden. Flame projection created atmospheric carbon monoxide concentration while impossible, generating rations that affected tunnel networks, extending beyond visible flame contact. The thermal effects that intelligence reports had described as localized damage proved defensive capability across entire underground complexes through acted positions. Corporal Morrison atmospheric contamination that forced evacuation of Intercon maneuvered the Sherman across terrain that revealed tactical limitations inherent in specialized equipment designed for specific combat applications rather than general Japanese positions, the tunnel construction purpose military operations. The flame projector's limited traverse required tank positioning that exposed vehicles to enemy fire from vehicles already struggled with the multiple directions while reducing mobility across volcanic terrain where track material, created by loose surface tactical employment, demanded accepting vulnerability that conventional tanks could avoid through superior mobility and longer impact of flame weapons engagement ranges. The psychological extended beyond immediate reaction problems, tactical effects into strategic influences that affected Japanese defensive morale throughout the island's garrison. Intelligence intercepts revealed enemy communications describing thermal weapons as violating traditional combat expectations while creating tactical conditions techniques. The fortress warfared not defeat through conventional defensive that underground construction co-effective against American assault methods during that had proven previous Pacific operations, encountered weapons that transformed protective positions into tactical liabilities, requiring fundamental changes in Japanese defensive doctrine. Staff Sergeant Chen's pressure monitoring revealed fuel system performance that maintained operational capability, while combat vibration created mechanical stress affecting components designed for static enemy fire. The hydraulian retesting rather than mobile operations, underic systems that regulated napalm flow operated within acceptable parameters, while electrical ignition maintained reliability despite environmental conditions that exceeded developmental specifications. American engineering had created weapons that functioned effectively under tactical employment that surpassed factory testing protocols. The tactical coordination that evolved during initial flame tank operations emphasized combined arms integration that maximized thermal weapon effectiveness while compensating for operational limitations through supporting infantry coordination. Fires and conventional Sherman tanks provided long-range suppression while flame variants could neutral maneuvered into effective positions where thermal projectionized targets that standard weapons could not affect. Detonated preparatory fires. Artillery observers that suppressed secondary positions while flame attacks eliminated primary defensive emplacements through thermal rather than explosive effects defensive adaptation. Japanese construction became apparent as enemy forces modified tunnel alternate ventilation systems that reduced thermal weapon effectiveness. The underground engineering that American intelligence had underestimated proved capable of tactical evolution that countered flamed compartments that include seal warfare through construction techniques specifically designed to defeat thermal weapons. Fortress reduction required sustained flame attacks that exceeded fuel capacity limitations while demanding tactical coordination that strained communication systems operating under combat stress. The resupply operations that became necessary by midday revealed logistical vulnerabilities that threatened sustained flame tank operations against defensive complexes requiring extended thermal attack duration. Fuel trucks approaching forward positions faced enemy fire that made resupply operations tactical challenges rather than routine maintenance procedures. The specialized nature of napalm handling created safety requirements that complicated field refueling while dangerous for support stat enemy artillery Meidainery operations vehicles carrying volatile swept by Japanese observation terrain cargo across contamination while maintaining operational capability through protection against atmospheric.